Welcome to this session on kinetic reactors. Kinetic reactors in Aspen Plus are the reactors that require the kinetics for the reaction. And so the having the kinetics in the reaction or the reactor, it adds an additional limiting term. So now it's not just the equilibrium limitations, right? So the equilibrium limitations might be there, but the kinetics talks about the rate of the reaction. And if assuming it's for a batch system, for instance, then we'll, we- we'll be dealing with time as a factor now. Time will limit the reaction. So the reaction might occur, but because it proceeds at a certain rate, it means how much time we afford the reaction will determine how far it goes. Right? And if it's for a continuous system, then that might be the weight the weight of catalyst in the reactor or the volume of the reactor, right? Which moves into space-time as well. So in order to run this or to use these reactors, you need specific details about the kinetics of the reaction, right? And the person must understand how these reactors operate, the fundamental principles of the reactors to have a fair idea of to have any good idea of what to do, how an understanding of what happens when you solve some of these problems. Well, Aspen, when it comes to these reactors, explaining the kinetics of these reactors, Aspen has fixed units that it uses for solving these problems. And sometimes it's problems with these units that makes working with these reactors complicated. So the units for homogeneous reactions, reactions occurring in just a single phase, it may be a liquid phase reaction or a vapor phase reaction, depending on the order of the reaction, the units as such. So if the order is 1, for instance, then you are just left with the system. So that's for a first order reaction. So N stands for the order of the reaction. And depending on whether the driving force is concentration or pressure, one of these forms are used when it's concentration, and here when it's pressure. And so you can see here. Then if it's a heterogeneous reaction, reaction occurring in more than one phase. So a good example would be a reaction occurring in the presence of catalyst, where both phases are different. So maybe the presence of a solid catalyst, while the reacting medium is liquid or gas or vapor phase. Then you might have to use one of these depending on whether it's concentration or pressure. Again, the N stands for the order of the reaction. Right. So the first reactor we are going to look at is the continuous stirred tank reactor, the Cstr, and these are some of the design equations regarding these reactors. So conventional, there's a mass balance, material balance reaction. And this is the Arrhenius equation for the temperature dependence of the rate constant for the reaction. And this is the energy balance equation, depending on whether the system is adiabatic or there's heat exchange involved. Some of these terms might be present or absent. Right. So the key things required to work with this reactor in Aspen is knowledge of the volume of the reactor, which again will depend on your understanding and ability to work with this, the pressure, operating pressure or condition for the reactor, the reactions and their rate laws, the Arrhenius parameters, and then the temperature or the duty. We are going to attempt a problem in Aspen Plus using the CSTR model. Here we have an irreversible endothermic vapor phase reaction following an elementary rate law. And the elementary rate laws, right, they are a consistent form where the rate of the reaction equals the reactant constant times the concentration of the reactants raised to their stoichiometric coefficient. Right? They have an exponent which equals the stoichiometric coefficient of that reactor. So whenever elementary rate laws are almost always power law models. So where you have an R equals K C, assuming this was component A, then you have R equals K C A. So whatever the coefficient of this, in this case is 1. So the concentration of A has an exponent of 1. The feed is pure acetone and is fed to the reactor at a given rate and a certain condition. And here we have the reactor volume and the entrance temperature. We have to calculate the conversion and temperature of the reactor depending on one of two configurations, whether it's operated adiabatically or isothermally. And here we have the Arrhenius expression for the rate constant. So we go into Aspen and enter our components. In specify the property method as here we are using an RTL property method. You can head to the simulation environment, which is the model palette, RCSTL. Add the feed and product streams. We're feeding this at a rate of 10 moles per minute. And the operating conditions to, sorry, so 2 atmospheres of pressure. And it's pure acetone. That should do it. Specify the reaction, the reactor operating conditions. So, and since we are running it adiabatically, we choose to specify the duty, where duty of 0. The specification type is the reactor volume in liters. It's 500 liters. That should be it. So there is the option to add the reaction here under the kinetics tab. Right? You can come to new and add a reaction, but we are going to go through the general way of adding reactions in Aspen Plus. So when you come to the pane, the navigation pane on the left, you see this, the reaction on the menu. So if you click on that, you're able to add a new reaction. So we call that R1. And we choose the type of reaction. It's a power law model. Right? We choose that. And that takes us to this sheet. It's where we add our reaction. Since it's a power law model, we specify our reaction type as kinetic. Okay. We have acetone. So coefficient of -1. And the exponent, right, is what determines the presence or absence in the power law model, in any part of the power law model. Right? So its exponent here is 1. Because it's right, and we can add our products. The coefficients of 1 of their products. And because they are absent in our power law model, the rate of reaction equals K times the concentration of acetone raised to its stoichiometric coefficient. Right? So that power here, or the order, so the reaction here is 1 with respect to acetone. And that's what's key in the exponent here. So this is what tells Aspen that acetone is present in the power law model. And it has an exponent of 1. Since we do not have the products there, the exponents are 0. If you also leave it blank, it will assume it's zero, and the reaction does not depend on that component. You could specify zero or leave it blank. It should work either way. That's how you add the reaction. And once you are done, you go to the kinetic tab, and it asks you for certain parameters, mostly the basis for the calculations. Right? So the phase, the volume, the phase of our reaction was vapor, and the basis is the volume of the reactor. So the Arrhenius parameters are entered here. This is where you specify the Arrhenius parameters, and they are in two forms. This is the most usual form. This is the form we have in the problem, but we are missing the T10. Right? And as a result, the exponent of the T10 is zero. Right? That's how the software knows that the T10 is not present in our model. Right? So n stays at zero. Then we have to express this in this form. Right? We need to specify the activation energy, E, and the K, the pre-exponential factor. Right? So we modify our problem, the K in our problem, using a bit of mathematics. We express this as a product of two exponents, and compute this first value, and that becomes our pre-exponential factor. And when we compare this side of this equation, we compare this to what we have here for the kinetic factor, we can see that the small k is the 8.197 times 10 exponent 40, and the other 10, which is the exponential function to the power, right, e over rt. You can see that e over r is a 34222. We have t down there. So that, since the value for the molar gas constant is known, we can estimate the activation energy. So we go ahead and enter the parameters as calculated. It's not even necessary. And then our activation energy. The units are kilojoules per mole Kelvin. And once we are done with that, we have entirely specified or entered our reaction into Aspen Plus. We can go back to our reactor and back to the kinetics tab, and that reaction should be present or available. Like I said, it could have also been created and added here. But this is the general form for any problem to solve. This is the general way of adding reactions in Aspen. So we can just move it from available to selected by clicking on this, and that should complete the specifications for our problem, and then we should be able to run the simulation. Good. We have results. And go to the block result and see. Remember, the temperature at which we fed our material was 1100 Kelvin, and the outlet temperature for the reactor is 879. Meaning we have lost some heat to the reaction due to the endothermic nature of the reaction. And if we go to the stream results, we can see all that is required to calculate or estimate our conversion. How much we've been able to convert based on what was fed and what came out. We are able to do that, and we see that we have a fractional conversion of about 0.3 9. And the next thing will be to solve the problem in the other way by specifying the exit temperature. We want to maintain the temperature at the inlet, 1100 Kelvin. We can run the simulation. And then when we go to the block results, we see that we have maintained that temperature at the expense of some heating requirements. We needed to supply some heat to the reaction medium to maintain the temperature. And we can go back to the stream results. And we observe that we have converted much. We have much less of the acetone coming out in our outlet stream. They've converted much more. And if you have the background in reaction engineering or kinetics, you would understand why this is happening. How the heat of reaction affects the temperature, the reacting medium, and how that in turn affects the reaction rate constant for the reaction. So that is all for the Cstr. We will be looking at the other reactor types, kinetic reactor types, the PFR and the PBR, the packed bed reactor and the black flow reactor in our next lesson. Thank you.